Welcome to today's paper reading. Today's paper is titled, ConvNets Match Vision Transformers at Scale. This paper was published on AR14 by Samuel L. Smith and colleagues from Google DeepMind. In this study, the authors pre-trained ConvNets on the large dataset JFT4B, using compute budgets ranging from 0.4K to 110K TPUV 4 core hours. They observed a log-log scaling law between the held-out loss and the compute budget. After fine-tuning on ImageNet, the ConvNets, specifically from the NFNet model family with increasing depth and width, matched the performance of vision transformers with comparable compute budgets. The strongest fine-tuned model achieved a top 1 accuracy of 90.4%. Convolutional neural networks, or ConvNets, played a crucial role in the early successes of deep learning. They were first commercially deployed over 20 years ago, and have since dominated computer vision benchmarks. However, in recent years, vision transformers, or VITs, have increasingly replaced ConvNets. These VITs are often pre-trained on large, general-purpose datasets, raising questions about their performance compared to ConvNets under similar computational budgets. Our research focuses on evaluating the scaling properties of the NFNet model family, a pure convolutional architecture, and comparing it to VITs under various compute budgets. Figure 1 illustrates the ImageNet top 1 error rates for NFNet models after fine-tuning for 50 epochs. The graph uses a log-log scale to show how performance improves with increasing pre-training compute. Notably, the largest NFNet model, F7+, achieves performance comparable to that of pre-trained vision transformers, VITs, with similar compute budgets. Additionally, the performance of the F7 Plus model is further enhanced when fine-tuned with repeated augmentation, RA, demonstrating the effectiveness of this technique in improving model accuracy. The authors trained a range of NFNet models on the JFT4B dataset, varying both depth and width. These models were trained across different epoch budgets, from 0.25 to 8 epochs, using a cosine decay learning rate schedule. The TPUV4 cores used in this study have roughly double the theoretical flops of TPUV3 cores, but both types share similar memory capacities. Performance metrics, such as ImageNet top 1 error, were evaluated, showing that as the compute budget increases, performance improves consistently. This improvement is comparable to that observed in pre-trained vision transformers, VITs. Figure 2 illustrates the held-out loss of NFNets on the JFT4B dataset, plotted against the compute used during training. Both axes are log-scaled, and each curve represents a different model trained for a range of epoch budgets. The figure reveals a clear linear trend, consistent with the log-log scaling laws observed in language modeling. This trend indicates that as the compute budget increases, so does the optimal model size and epoch budget, achieving the lowest validation loss. The figure also highlights that a reliable rule of thumb is to scale both the model size and the number of training epochs at the same rate, similar to what has been observed in language modeling. Additionally, the figure notes that the optimal epoch budget was greater than 1 for compute budgets exceeding approximately 5K TPUV 4 core hours. Figure 3 illustrates the predictable behavior of the optimal learning rate across different epoch budgets for 3 models. Initially, all models exhibit a similar optimal learning rate of approximately alpha is almost equal to 1.6 when the epoch budget is small. As the epoch budget increases, the optimal learning rate decreases, particularly more rapidly for larger models. This trend allows for efficient tuning of the learning rate with just 2 trials, assuming a slow but monotonic decrease as both model size and epoch budget grow. In terms of pre-training efficiency, the NFNet F7 Plus model required 110K TPUV 4 core hours, which is competitive with the 120K TPUV 4 core hours for ViTG/14 and 280K TPUV 4 core hours for ViTG/14. During fine-tuning, the regime consistently favored slightly larger models and smaller epoch budgets, suggesting that larger models have more capacity to adapt to new tasks. Interestingly, the pre-trained checkpoints with the lowest validation loss on JFT4B did not always achieve the highest top 1 accuracy on ImageNet after fine-tuning, indicating that the fine-tuning process itself plays a significant role in final performance. In this discussion, The authors emphasize that the key determinants of a model's performance are the computational resources and the data available for training. They highlight that while vision transformers, VITs, have shown impressive results in computer vision, there is insufficient evidence to conclude that they outperform convolutional neural networks, ConvNets, in a fair comparison. However, VITs may offer practical advantages in specific scenarios, such as their ability to use similar model components across different modalities, which can be beneficial in multimodal contexts. The authors acknowledge the contributions of Lucas Bayer and Olivier Henaf, who provided valuable feedback on an earlier draft of this note. Additionally, Lucas Bayer is thanked for providing training speed estimates for vision transformer (VIT) models on TPU-v4 devices, which has been instrumental in the development and optimization of these models. Thank you for watching.